ሰላም ለእናንተ ይሁን። ዛሬ በዚህ ቪዲዮ ይዤላችሁ የቀረብኩት የቤዚክ ማትማቲክስ ሚድ ኤግዛም ሶሉሽን ለሶሻል ሳይንስ ተማሪዎች ይሆናል። ስለዚህ እነሱን ጥያቄዎቹን አንድ በአንድ ለማየት እንሞክራለን። ስለዚህ በቀጥታ ወደ ጥያቄዎቹ ከመሄዳችን በፊት ምናልባት ለዚህ ቻናል አዲስ የሆናችሁ ልጆች ካላችሁ ቻናሉን ሰብስክራይብ እና ቪዲዮን ደግሞ ላይክ ማድረግ እንድትጀምሩ አበረታታለሁ። ይህን ካልኩ በኋላ ወደ ጥያቄዎቹ በምንሄድበት ጊዜ የመጀመሪያው ጥያቄ ወይም ደግሞ የመጀመሪያው ፓርት ትሩ ፎልስ ፓርት ነው። So it says determine whether each statement below is true or false, it says. So when we start from the first question, that's question number 1 says, if X is an element of A union B and X is an element of B complement, then X is an element of A. So that just to do this, we know that given X is an element of A union B means this X must be an element of either of these two sets, that is, X is an element of A or X is an element of B. Or X can be common element of A and B both. So that also X is an element of B complement means X is not an element of B. So that if X is not an element of B and if X is an element of the union of A and B, so that the only possibility for X to be within the union of these two sets could be X must be an element of A. So that here, that is the statement if X is an element of A union B and X is an element of B complement, then X is an element of A could be a true statement. So that the answer for the first question is true. Second question, question number 2, if Q is a false proposition and P is a proposition, then Q implies P is always true. Remember the rule that must be applied for just to determine the truth value of a logical implication of this form, that is Q implies P. So that in this case, if we see this one by using or simply preparing a table, we have Q and P, which are the component or propositions for this logical implication. But what we are informed here is Q is always false, so that the possibility for the truth values of Q implies P could be, it can be false implies false or false implies true, which is always true. Therefore, the statement if Q is false proposition and P is a proposition, any proposition, that means then Q implies P is always true, is always because as we can observe from this one that simply Q implies P is always true, whatever the truth values of P here is because Q is always a false proposition. Then when Q is false, Q implies P as true, regardless of the truth values of the second component proposition, that's simply P, so that the statement is true. Question number 3. If the set containing 1 is the subset of the set containing -1, divide the set containing 1. Then we know that this set is containing 3 elements, which are -1, which is a number, 0 is also a number, and the set containing 1, that is the set containing the number 1. Then for the given set, the first set, that set containing 1 to be the subset of the subset, every element of this set, the given set must be an element of the second set. But the element of 1 is 1, and the element containing the element containing the set containing 1 is 1, and but this one, that's simply 1, which is the element of this set, is absent within the second set, that's simply this set, so that this set cannot be the subset of the second set. Therefore, the statement is false. Therefore, the answer for this question will be false. Okay, question number 4. If A the subset of B, then the intersection of these two sets, that is A intersection B, is empty set. We know that if A is the subset of the second set, that's simply set B, means every element of the first set, that's simply set A, is also an element of this one, that's simply B, or B includes every element of the first set, that is A. So that the definition for the subset of this one, simply subset of the first set to be the second set. Therefore, A intersection B is equal to empty set, A, whenever A the subset of B. It is not empty set, so unless the given set that simply A itself is empty, therefore the intersection of these two sets will be A if A the subset of B. Just if we consider a counter example for this one, let's assume that A is containing one element and B is containing 1 and 2. Clearly A the subset of this one, that's simply set B, because the element of A, which is 1, is also an element of B. So that A but the intersection of these two is 1, which is different from that of empty set. Therefore, this may not be unless this one that is A itself is empty set. The intersection of these two, intersection B must be A. Therefore, the statement is that is false. Question number 5. The truth value for every x, an element of n, the equation that is 3x minus 2 is equal to 0 is false. We know that this is universal quantifier. This statement will become true if and only if the statement that is 3x minus 2 is equal to 0 is satisfied or simply becomes true for every x which is a natural number, or simply for all natural numbers. But any the set of natural number that usually this one that's simply set containing 1 to 3 and other positive natural numbers, so that when we solve the equation that is simply the statement 3x minus 2 is equal to 0, this will be satisfied or simply becomes true whenever x is equal to 2 over 3. But we know that this one that's 2 over 3 is not a natural number. A natural number, that means there is no any natural number that can make this statement to be true, even 1. Therefore, since there is no natural number satisfying the equation, the universal statement is false. Therefore, the statement for this one is that is simply true, because it says the truth value for every x an element of n, 3x minus 2 is equal to 0 is false, so that it is true. Okay, they hit the first question, the first part, and second item, or simply part of this exam could be multiple choice item. The general instruction for this item could be choose the correct answer and write the letter of your choice. It will weighs 2 pointers each. So that the first question could be the negation of milk is white is A, milk is not white, milk is blank, and B, and none. We know that the negation of the statement is simply will be obtained by negating the predicate, or simply the given statement itself. So that milk is white has a negation. The opposite, or simply the negative of milk is white, could be just milk is not white. Therefore, the best alternative, or simply the correct alternative for this problem or simply question could be, and that is A, which is milk is not white. Therefore, the answer could be milk is not white, which is with alternative A. Question number 2. Which of the following is an open proposition? A, x plus 1 is equal to x plus 1 less than x plus 1 is equal to 0. There is an alternative that's simply D, that is all. So in order to have a solution for this one, or simply just to determine which alternative is an open proposition, you know what an open proposition is and closed proposition, so that a statement that contains a variable and becomes a proposition when the variable is assigned and then the assigned value is an open proposition. So that which of the given statements or simply alternatives here will satisfy the condition or simply the definition that already we defined here. We know that when we see the first one, that simply x plus 1 is equal to x, it could be simplified as 1 is equal to 0. That means if we take this one to the right side and subtract from this one, x minus x will become 0. 1 is equal to 0. It doesn't have or simply involve a variable, so that is closed statement. Therefore, his which is always a false statement, so that it is not open, rather it is closed proposition. Similarly, the second one, that simply be x plus 1 less than x it can be simplified as 1 less than 0 when by subtracting x from both sides of this inequality, so that which is always false again. Therefore, this statement is also, it is not open, rather it is closed proposition. And lastly, that is C, x plus 1 is equal to 0 depends on the truth value of this one, that simply x plus 1 is equal to 0 depends on the value which we can replace the variable that is x here. So that this one, that simply because the truth value of this one cannot be determined unless we replace the variable that is x by a certain value. Therefore, this proposition will becomes or simply satisfy this definition. Therefore, this is an open proposition. Therefore, the answer for this statement could be, that is C. All are not correct since C is the only one, so that C will be the correct answer for this problem or simply this question. Question number 3. Which of the following proposition is equivalent to P implies Q? We are given a logical implication P implies Q, and we are asked just to select which alternative is equivalent to that of this one, that simply P implies Q. The first thing that we can observe here is that we know that this one, that simply P implies Q, is equivalent to the negation of P, or this one, that is Q. So that in the first case, that's simply A. The alternative which we are given here could be the negation of Q implies negation of P, which is directly the contrapositive of P implies Q, and the contrapositive and the given logical implication are equivalent to each other, so that negation of Q implies negation of P is equivalent to P implies Q. Similarly, the second one, that's simply P, we have negation of P and negation of Q is equal to negation of P or negation of Q using that of De Morgan's law. Therefore, these two are equivalent to each other. Even separately, these two are equivalent to this logical implication, that is P implies Q. So that negation of P or Q is also equivalent to this logical implication, which is P implies Q. C, negation of P or Q means when we distribute this one again by using that of De Morgan's law, negation of P or Q, or which we have seen or simply which we have here, is equivalent to that of the given logical implication, that is P implies Q. Therefore, all these three are equivalent to this logical implication, which is P implies Q. Therefore, all are equivalent to this, and the answer for this one could be D, which is all of the above. Question number 4. Let A and B be sets with A the subset of B. Which one is not true? We are given A and B be any sets or simply sets with satisfying the condition where A is the subset of B or B includes A. Then which one is not true is the question. What we are given here is, we are given that is sets A and B satisfying the condition that is A the subset of the second set, that is set B. So that in the first case, A intersection B is equal to B minus A. We know that A is the subset of B, so that if A is the subset of B, A intersection B cannot be B minus A, rather it must be A. Since A is the subset of B, or simply every element of A is also an element of B. Therefore, B minus A is simply B without A, which is not equal to that of this one, that's simply B minus A, or A itself. Therefore, this alternative, that is intersection B is equal to B minus A, is a false alternative, or simply false. Similarly, the second one, that's simply B, A minus B is equal to A. We know that A minus B, that is A without B, but what we are given here is A, the subset of B, so that A minus B cannot be A, rather it must be empty set. Because A, the subset of B, so that A minus B must be empty. It is not A unless A itself is an empty set, so therefore the second alternative, that simply B, is also false. C, A union B is equal to B. A, the subset of B, so that the union of these two sets must be the larger set, that simply set B, so that there is a true statement. And lastly, that is D, A intersection B is equal to A, the subset of B, so that the intersection of these two sets must be the smaller set, that is A, therefore this is also true statement. Therefore, the statement which is not true here is that, and that is even though in that of B are false, but with a certain restriction, that simply B will be false only when that is this one, that is because we have a restriction, that is unless A is equal to this one, which is implicit. Therefore, the best and correct answer for this alternative, that simply question number 4, will be the first one, that is A, that is A intersection B is equal to B minus A, it is not true, since A the subset of B, so that the answer is sorry, it is not D, rather it is, and that is A. This is not the alternative, that is the best alternative, is that is A, that which is intersection B is equal to B minus A. So that the answer. Then the next question, question number 5. Question number 5 will be the contrapositive of, if two sets are equal, then they have the same number of elements. What we are given here is, we are given a logical implication. If two sets are equal, then they have the same number of elements. Then we know that the original statement is, that is logical implication, which can be written in the form of P implies Q, where P, that is the if statement, is two sets are equal, and second statement, that's simply the conclusion, which is Q, is they have the same number of elements. We know that the contrapositive of this statement, or the logical implication, will be obtained by interchanging and taking the negation of the component statement as P implies Q. That is, if we are given this logical implication, the contrapositive of this logical implication could be the negation of Q implies negation of P. Therefore, if P and Q are given here, or simply extracted like this, then the contrapositive will be negation of Q implies negation of P, but one negation of Q could be two sets have different number of elements. That means Q, they have the same number of elements, so that the negation of they have the same number of elements could be considered as two sets have different number of elements. Similarly, the negation of the if statement of the original logical implication, which is P, that is two sets are equal, could be they are not, or simply the two sets are not equal. Then when we combine these two negations by using that of implication, we'll obtain the contrapositive of this logical implication. Therefore, the connected contrapositive could be, if two sets have different number of elements, then they are not equal, or simply they are not equal sets. So that this could be directly the contrapositive of if two sets are equal, then they have the same number of elements. Therefore, the answer for this could be alternative C, so that the answer is C, which is if two sets have different number of elements, then they are not equal. They are not equal. Question number 6. Which one of the following is true? A, empty set is the proper subset of A. For any set A, you know that for any set A, logically, we know that every set cannot be the proper subset of itself. But every set can be the subset of itself. This is always true, but this may not be true, always true whenever, for example, that is A's empty set. Therefore, empty set cannot be the proper subset of itself, so A is false. Similarly, B, A minus B is equal to B minus A. That is, difference between two sets cannot be, or simply generally cannot be equal sets unless the two given sets are equal sets. That means the only possibility for A minus B and B minus A to be equal is that individually the given sets A and B needs to be equal to each other. Unless these two sets are equal, the difference between A minus B and B minus A cannot be equal sets, so that this is generally a false statement. Next one, that's simply C. If this one that is A minus B is equal to empty set, then A is the subset of B. We know that if A minus B is equal to empty set, it means that either A is the subset of B, or this one that is A can be empty set itself. Therefore, if A is equal to this one that's simply empty set, every element of A is in B, which implies A is the subset of B, so that this statement is true. And the last, so that the answer for this one could be alternative C, which is A minus B is equal to empty set. That is, if A minus B is equal to empty set, then A is the subset of set B. Okay, the third part, or simply third item, it is fill in the blank space. Then question number 1, the truth value of for some x, an element of R, and for every y, which is an element of R again, x plus y is equal to y is blank. We know that this statement, or simply quantified proposition, would become true if we can obtain at least one x, or simply some x, which holds true for every real number y in satisfying the condition of x plus y is equal to 0. Therefore, when we do this, we know that x plus y is equal to y can be simplified to x is equal to this one that's simply 0. That means when we subtract y from both sides of this equation, that which holds true for all y, and then we can obtain that simply for some x, an element of R, x equal to 0 is true. Hence, let's check, for example, that simply that there exists an x such that for all y, x plus y is equal to 0. The answer for this one could be yes, because if we take x equal to 0, which is the additive inverse in the set of real number, it works because 0 plus y is equal to y for all y, so that we can obtain at least a fixed x, that simply x is equal to 0, which holds true for every real number y in satisfying the condition of x plus y is equal to 0, so that the statement is true. So that the truth value of the given statement, or simply quantified proposition, will be true. Next question, question number 2. If, or simply let, number of A without B is equal to number of B without A, which is equal to X. They have the same number of elements, and the number of elements of their intersection, that is intersections, B is equal to Y. Then the number of A union B is equal to blank. So that in order to relate the number of elements of A union B and number of A minus B b minus a and their intersection. Let us see this one, or simply it could be clearly visible by using that of the application of Venn diagram. But mathematically, we can illustrate this one as a minus b elements in A, that is those elements that are contained in A but which are absent in B would be, that is X, which we are given here. Similarly, for second one, that's simply B minus A, those elements that are contained in B but which are absent in A, which are elements of B only, which are equal to that of the first one, which is X again. Then the number of intersection, that is intersection B, that is elements in both A and B are given to be this one, that is Y, because we are given here. Then the number of A union B is equal to the number of those elements that are contained in A only plus in B only plus the intersection of these two. So that when we substitute the given values X and that of Y within this equation, we can obtain the number of elements of A union B, which is equal to X plus, that is number of A minus B is X, which are equal to each other, and number of B minus A is also X, plus the number of their intersection is Y, so that X plus X, which is 2X plus Y. Therefore, the exact answer for this problem could be 2X plus Y. The next question, that is question number 3. If P implies Q is equivalent to negation of P or Q, then the truth value of P implies Q if and only if negation of P or Q is blank. We know that this is a logical by implication, and which depends on these two equivalent propositions, simply compound propositions. We know that the statement P implies Q, the statement says P implies Q is equivalent to that of negation of P or Q is true by definition because they are equivalent to each other. And from the definition, or simply the property or the rule of biconditional, or simply by implication, the biconditional P implies Q if and only if negation of P or Q is true whenever both the component statements or simply propositions have the same truth values. That means either both P implies Q and negation of P or Q are true, or P implies Q and negation of P or Q are false at the same time. That means, therefore, since they are logically equivalent, the biconditional is a tautology because they have the same truth values. That simply both P implies Q and negation of P or negation of Q, because they are equivalent. We know that two compound statements are said to be equivalent whenever they have the same truth value for every assignment of their truth values of their component statements. Therefore, they have the same truth value. Therefore, this one that simply P implies Q and if and only if negation of P or Q is always true, so that we can consider this compound statement as its tautology. But what we are given here is we are asked just to find the truth value of this compound by implication, and therefore the truth value for the given compound statement could be true. The next question, using the partial listing method, describe the set containing X, an element of Z such that X is less than or equal to minus 3 implies X squared is equal to 9. That means the solution set of this logical implication with the equation which connected the equation that is X squared is equal to 9 and the inequality that is X less than minus 3 whenever X is an integer. Therefore, the condition that is X less than or equal to minus 3 implies X squared is equal to 9 could be true. That simply this is P implies Q is true whenever P is false or Q is true, or whenever both these two have the same truth values. Therefore, let us consider, or simply let us see by considering or simply cases. In the first case, let's assume that this one, the first one, that is X less than or equal to minus 3 is false. If this one is false, for this logical implication to be true, x squared is equal to 9 can be either true or data false, because both false implies true and false implies false are true. Therefore, those real numbers that can make this statement to be true could be an element of the given set. Then this is false, which implies x is greater than this one, that's simply 3. All integers greater than that of minus 3. All integers greater than that of minus 3 can satisfy the condition. That means for x less than or equal to minus 3 to be false, or simply those real numbers or simply values of x that can make x less than or equal to that of minus 3 to be false, is that whenever x is greater than that of minus 3. Therefore, they said that is x minus 3 can make this statement to be false. So that whatever x squared is equal to 9, always x greater than minus 3 could be integer, all integers greater than that of minus 3 could be an element of this set. And then the second case could be when we assume that both needs to be true, that is x less than or equal to minus 3 and x squared is equal to 9 can be true at the same time for the given logical implication to be true. But we know that x less than or equal to minus 3 is true. It needs x squared is equal to 9 to be also that simply is true. Therefore, x is equal to minus 3 could be the only integer that can make both these two, the inequality x less than or equal to minus 3 and the quadratic equation that is x squared is equal to 9 to be true. Therefore, here we have set of integers that are x greater than or greater than minus 3, and here we are we obtained already that is simply x equal to minus 3, so that the union of these two could be the set containing x is equal to minus 3, that is minus 3 less than or equal to minus 3, which is true. Minus 3 squared is equal to 9, so that works. Then the solution set could be integers greater than or equal to that of minus 3, which is using that partial listing method, that is set containing minus 3, minus 2, minus 1, 0, 1 to 3 could be the answer. Okay. The last question, that is the last question item, that means, which is workout. We have two questions containing 3 pointers for each. The first question could be, determine whether the following proposition is tautology, contradiction, or neither. Remember the condition that must be satisfied for the given compound proposition to be tautology or contradiction, or neither of these two, that is neither tautology or contradiction. We know that whenever all the truth values of the given compound statement is always true, whatever the truth values of its component statements are, so that compound statement is said to be tautology. It becomes contradiction whenever the truth value of the given compound proposition is always false, whatever the truth values of its component statements or propositions. Therefore, in order to determine whether the given statement is a tautology, contradiction, or simply neither, we can use the application of that of a truth table. To do this, because we have given, or simply we are given this compound statement, which is very long, so that let us see, or simply let us use just the assignment for the component statement is for the compound statement. You know that we have 3 variables p, q, and that of r, that is simple propositions, so that the given table, or simply the truth table for this compound statement may have to the power of 3, which is 8 rows. And let's assume that capital letter P stands for the first if statement of this logical implication, which is negation of P and Q, or negation of R. Similarly, the second, let us represent the second, this one, or simply the logical by implication by capital letter Q, which stands for negation of Q if and only if P. Then what we we can evaluate here that if we replace P, this one by P, and this one that's simply negation of Q, if and only if P by Q, we have this statement depending on P and the data of Q becomes P implies Q. So that the truth value of P implies Q will determine whether this logic or simply compound statement is tautology, contradiction, or neither. Then the truth value could be first, the simple statement, the three simple statements could be P, Q, and that of R. Sorry. We have also negation of R, because negation of R is here. Q or negation of R, Q or negation of R. We have P. P stands for totally, that is negation of P, and Q or negation of R. We have negation of Q, this one, negation of Q implies, if and only if P. We should this one, so for we have P, capital letter P implies Q, which is the given compound statement, the original compound statement, which is this one. Therefore, depending on the truth values of the simple three statements P, Q, and that of R, we have, for example, if everything or simply all the three simple statements are true, negation of P could be false, this is false, Q or negation of R, Q or negation of R is true because Q is true here. We have P, P stands for the first one, that's simply this one, negation of P or Q or negation of R, we have true here, negation of P is this one that's simple, so that false, and true is this one that's simply false. Negation of Q is false, so that negation of Q, if and only if P could be false because P is true here. So that P implies Q will be, that is, the truth value of the given original compound statement is true here. Similarly, second possibility could be whenever the first two propositions are true and the third that simply R is false, the compound statement that simply P implies Q is true. Whenever the first one is true and second Q is false and R is true, so that P implies Q or the original compound statement is again true. Even whenever only the first one is true and the rest Q and R are false at the same time, P implies Q is also true here. Then all the 8 possibilities will be this one. Therefore, in order to determine whether the given proposition or simply compound statement is true or simply false here, we have to observe the truth values of this element. We know that the truth values of this element or simply P implies Q, which was the compound statement that's simply negation of P, and Q or R implies a negation of Q if and only if P. It is true for some instances and it is also false for the other case. Therefore, this compound statement is neither tautology nor contradiction. It is neither tautology or contradiction. Therefore, the compound statement is, because the element of this one that simple P implies Q has both a true and data false values. Therefore, the compound statement is neither tautology nor contradiction. That means. Okay, the next question or the last question for this session, question number 2. Shortly or simply in combined or simply in simplest way, the question will looks like or simply can be written in this way. 50 cars belong to an enterprise that has 3 departments A, B, and C. That means there are 3 departments A, B, and data of C, and within this department there are 50 cars belonging to each departments. 6 cars are available for all 3 departments. That is for all A, B, and that of C, there are 6 cars out of 50 which are available for all the 3. 2 cars give service to neither of the department. Out of the 50 cars, there are 2 cars which doesn't serve any or simply give any service for neither of these 3 departments. Then 24 cars are administered by Department B. Also 16 of them are also used by the other departments. There are twice as many cars in Department A as in Department C. Equal number of cars are allocated when used by any 2 departments. Then, after we are given this information, what we are asked here is, we are asked just to define or simply just to find the number of cars administered by each department. That means number of cars administered in Department A, number of cars in the administered or simply belonging to that of this one, that's simply B, and number of cars administered in Department C. Therefore, in order to solve this one, let us represent the number of cars in each department by using that of a certain variable. For example, that is, let's assume that X be the number of cars that are administered in A only, which are absent in either B or C. That means there are X number of cars which are administered in the first department, that is simply A only. Similarly, let by B the number of cars administered in B only, which are not included or simply administered in either A or C here. And lastly, let Z be the number of cars administered in C only, and in the combination of these two, let U is equal to the number of cars that are administered in both A and that of B. That is A intersection B without C and B only, and B and intersection C or simply A and C only, be represented by using that of the variable that's simply B, and the number of cars administered in B and C only, be represented by the variable that's simply W, and T could be the number of cars administered in 3 departments commonly, that is A intersection B intersection C is equal to 6. All the 3, that is A, B, and that of C. Then equal number when used by any 2 cars or simply departments means the number of cars in A and B, A and C, B and C are equivalent to each other. And let's assume that U is equal to V, that is simply U stands for the number of cars administered in A and B only. B, U, V, W, B, a certain constant that's simply K, when K is the number of cars in either of in any 2 departments. Then the total cars could be the number of cars in A only, the number of cars in B only, the number of cars in C only, and the number of cars in A and B. This is in B and C or simply A and C. This is in any of the 2, that's simply 2, that means plus T plus 2 is equal to 50, when 2 stands for 2 cars which doesn't serve any of the departments. Then when we substitute this one, that's simply U plus U is equal to V is equal to this one, that's simply K, then we have this equation will be converted into X plus Y plus Z is equal to 3K. 3K stands for this is K, this is also K, this is also K, so that K plus K plus K could become 3K, plus we have this one that's simply T, which is 6. That is the number of cars in the 3 departments. 6 plus 2, which is neither of the 3, is equal to 50. So that from this we can have this is 8. If we take this one and subtract from 50, we have X plus Y plus Z plus 3K is equal to 42. let's call this one to be the first equation. And secondly, 24 cars are administered by B, department B, that means. So that Y plus U plus W plus T is equal to Y plus K, because K plus K in this case, that is U plus U, V and W are equivalent to each other, and they are represented by that of this constant, that's simply K, so that Y plus K plus 6 is equal to Y plus twice of K plus 6. This is 24, because the total number of cars administered in department B. Therefore, when we solve this one, that's simply if I take this one to the right side, we have Y plus 2K is equal to 18. And let us call this one to be the second equation. Similarly, 16 of B's cars also used by other department. 24 cars are administered by B, and from the 24 cars, 16 of them are used by other departments. So that U plus W plus T could be simply the same as K plus 6 is equal to twice of K plus 6, which is equal to 16. Therefore, we have 2K is equal to 2K plus 6 is equal to 16, or we have from the second equation, that is the second equation means from this equation, that is Y plus 2K is equal to 18. We can have Y plus twice of 10, twice of 5 is equal to 18. This implies Y plus 10, that is 2 times 5 is 10, is equal to 18, which implies Y is equal to 8. Therefore, but what is Y? Y is the number of cars that are administered in B only. In B only. Therefore, this is the first solution for the given problem. Now, we have this one, that is U is equal to V is equal to W is equal to 5. So that T is equal to 6 and Y is equal to 8. Then from 1 again, we have X plus 8 plus Z is plus 3 times 5 is equal to 42. From the first equation means, the first equation, this one, that is X plus Y plus Z plus 3K is equal to 42. We already obtained that is this one, that's simply Y to be 8, and K is 5, X is unknown, Z is also unknown, so that when we substitute these values in the place of the given equation here, we can obtain this one, that is X plus 8 plus Z plus 3 times 5 is equal to 42. So that we have 4 plus X plus 8 plus Z plus 15 is equal to 42, and 8 plus 15 is 23. So that when I transform this one and subtract from 42 here, we have X plus Z is equal to 19. And let us call this one to be the third equation. This is the third equation. Similarly, cars in A are X plus U plus V. That means the number of cars in A means, in department A means, the number of cars in A only, the number of cars in A and that of B, or the number of cars in A and that of C, and the number of cars in A, B, and that of C. So that we have X, the number of cars in any of the two are equivalent to that of 5, and this V is also 5 because they are equivalent to each other. 6 is the number of cars in the 3 departments, so that this is equivalent to X plus 16. Similarly, cars in C will be Z plus V plus W plus T, which is equal to Z plus 5 plus 5 plus 6 is equal to Z plus 16. ይሄ ማለት ነው እዚህ ሲ ዲፓርትመንት ውስጥ ያሉ መኪኖች ማለት ሲ ላይ ብቻ ያሉ በሲ እና በኤ መካከል ወይም ደግሞ በሁለቱም ላይ ያሉ ሁለቱም ላይ ሰርቭ የሚያደርጉ ማለት ነው። ወይም ደግሞ በሲ እና በቢን ሰርቭ የሚያደርጉ በሁለቱ ሰርቭ የሚያደርጉ ይሄ ቲ ማለት ደግሞ ሶስቱም ዲፓርትመንት ኤ ቢ እና ሲን ሰርቭ የሚያደርጉ ማለት ነው። ስለዚህ እነዚህ ስንደምራቸው ዊ ካን ኦብቴን ኦር ሲምፕሊ እዚህ ሲ ላይ ሰርቭ የሚያደርጉ ቶታል ነምበር ኦፍ ካርስን ይሰጠናል ማለት ነው። ስለዚህ ዜድ ፕላስ 5 ይሄ 5 ማለት በእያንዳንዱ በኤኒ ኦፍ ቱ በሁለቱ መካከልም ደግሞ ሁለቱንም ሰርቭ የሚያደርጉ እኩል ናቸው። በኤ እና በቢ እና በሲ ወይም ደግሞ በኤ እና በሲ ወይም ደግሞ ሲን ሰርቭ የሚያደርጉ መኪኖች 5 ናቸው በሶስቱም። ስለዚህ ቪ እና ደብሊው ኢንዲፔንደንት ወይም ደግሞ ለእያንዳንዳቸው 5 ነው። እነዚህ 6 ማለት ደግሞ ሶስቱንም ሰርቭ የሚያደርጉ ነው በጋራ ዲፓርትመንቶቹን ሶስቱን ዲፓርትመንቶች ሰርቭ የሚያደርጉ ናቸው። ስለዚህ ይሄ ዜድ ማለት በሲ ነምበር ኦፍ ካርስ ኢን ዜድ እንዳት ሲምፕሊ ሲ ኦንሊ ፕላስ 16 then twice as many as in A as in C አሁን ሌላ ምን ተብለናል? እዚህ ኤ ላይ ያሉት የዚህ ሲ ውስጥ ያሉትን 2 እጥፍ ናቸው። ስለዚህ ኤክስ ፕላስ ዜድ ማለት ኤክስ ፕላስ 16 ማለት that is the number of cars in Z, I mean in A, is equal to twice of the number of the total number of cars in C. That is x plus 16 is equal to twice of Z plus 32, that is 2 times 16. So that x minus twice of Z is equal to 16, that is 32 minus 16. So let us call this one to be the fourth equation. Then from the third equation, we know that the third equation means that's simply this one. So we have this one, that is x is equal to 19 minus z. 19 minus z. So that in this case, substituting into 4, that's simply here. 19 minus z is equal to 90 minus z is 90 minus z minus twice of z is equal to 16. Then 19 minus z minus twice of z could be minus 3z is equal to 16. This implies minus 3z is equal to minus 3. So that z is where z becomes 1. Then from 3 again, x plus 1 is equal to 19, which implies x is equal to 18. That is, if you subtract 1 from 19, it becomes the number of cars in A only becomes 18. Then when we summarize this one, we have this one, that is the number of cars in A only are 18, in Y only, and that is 8. In C only, that we have 1. U, that simply the number of cars in A and B is 5, in A and C is 5, in B and C is also 5, and the number of cars in A, B, and that of C. The number of cars that can serve all the 3 departments are 6, and none of out of this one we have 2 cars here. Therefore, the number of cars in A could be, that is the number of x plus u plus v plus t, 18 plus 5 plus 5 plus 6, which is 34. The number of cars in B, or the number of cars that can serve in department B, y plus u plus w plus t, which is 24. Number of cars in C, z plus v plus w plus t, 1 plus 5 plus 5 plus 6, which is 17. አሁን እዚህ ጋር ተመልከቱ። ነምበር ኦፍ እዚህ ኤ ላይ ወይም ደግሞ ዲፓርትመንት ኤ ውስጥ ኤን ሰርቭ የሚያደርጉት ነምበር ኦፍ ካርስ ሲ ላይ ያሉትን 2 እጥፍ ነው ብሎናል ተብለናል። ስለዚህ ኤ ላይ ያሉ 34 ናቸው፣ እዚህ ሲ ላይ ያሉት ደግሞ 17 ነው። ኤግዛክትሊ 34 is twice of this one, that's simply 17, so that it is correct, or simply we can check 34 is equal to times 17, and the total cars ያለን ስንት ነው? 50 ነው። ስለዚህ እነዚህም በሙሉ በምንደምርበት ጊዜ 50 መስጠት አለበት። 50 መስጠት አለበት። ስለዚህ ይህንን በምንደምርበት ጊዜ ስንት ነው የምናገኘው? 18 ሲደመር 8 ሲደመር 1 ወይም ደግሞ እነዚህን በምንደምርበት ጊዜ we can obtain this one that's simply 50. Therefore, the solution looks correct. So that number of A is equal to 34, number of B is 24, number of C is 17, because we are asked just to find the number of cars that are administered in each department. So that this is the answer for this problem. ትንሽ ረዘም ይላል። ስለዚህ በዚህ መልኩ ማየት ይቻላል ማለት ነው። Okay, that is all what I have for today.